Hello everyone, this is Dr. Hopkins with your next video. In this case, we're going to look at acid strength, or what makes one acid stronger than another. And obviously, that's going to be structure. So, let's start with this idea of our Bronsted-Lowry acid equilibrium. So our acid going to HCO plus and A minus, it has a Ka, right? So that's the equilibrium constant. Well, clearly, the larger that Ka is, the stronger or more dissociation we have. Remember, in the case of our strong acids, we don't even write it as an equilibrium. So I've looked up a few Kas. So HCl is one of our strong acids, or hydrochloric acid. And you can see that the Ka for that is 1.3 times 10 to the 6th. Okay, so it's a very large equilibrium constant, which means we're favoring products. We're going to take all of HA and make H3O plus. So HF, all right, so same row, it's a halogen. The Ka was 6.4 times 10 to the minus 4. We did a weak acid calculation in the last video using HF. And then acetic acid, CH3CO2H, the Ka is 1.8 times 10 to the minus 5. It's getting smaller, so the acid is weaker. HCN is 10 to the minus 10, so it's even weaker. So if we want to know what's the stronger acid, we can just mathematically look up the K, and that tells us exactly. So here we're going to weaker. But we can also look for, in the absence of these tables, we can look for clues in the structures. Right? So there's things that we know about structure, things we learned last semester that we can apply to understand acid strength. And so first, we've addressed this in previous videos, so only the hydrogens involved in polar bonds are considered acidic, at least in water. So that means that HO bond, or H is bonded to O, or H is bonded to N, or F, or Cl, are all possibly acidic, but an H bonded to carbon is not. Okay, that's because of the polarity of that bond. And then we're going to consider, so if we have a simple binary acid, so it's just the proton plus another element, X, for example, the stronger the bond, the weaker the acid. Right, so the short, or actually, and when we say stronger bond, we typically mean shorter bond. So the shorter the bond, the weaker the acid. And this makes sense because the acid is, if it's going to get rid of the H, the stronger the bond, the harder it is to get rid of that H to be acidic, to donate it. And so if we think about it, HF is a weak bond, is a weak acid. And if we were looking at the halogens, F is at the top of that column. It's the smallest of those halogens. Well, HCl would be strong. HBr would be even stronger. Okay. So what about some oxygen-containing acids? Right, so those are binary acids. The other kind of acids that we'll deal with typically are oxygen-containing, or oxo acids. So let's just consider something like HO and then X is some general element. So the more electronegative that X is, the stronger the acid. Okay? So remember, we're going back to what we learned in 105 about electronegativity. So judging based on the position on the periodic table, we can tell whether an element is more electronegative or not. And so why does electronegativity work? Because electronegativity, remember, is the ability of an atom to pull electrons to it in a bond. And so electronegative elements are going to pull electron density away from that hydrogen-oxygen bond, making it weaker overall, and also making it then a stronger acid. So if we consider, once again, our halogens, in this case, so HOCl, HOBr, HOI. So we're picking on that one column of the periodic table, which I'm not showing, but you can look up in your book or look up online. And chlorine is above bromine, is above iodine. Remember, if we go down the table, the electronegativity gets less, right? So the more smaller elements are more electronegative, larger elements are less electronegative. And so you can see the acid strength, 10 to the minus 8 for HOCl, 10 to the minus 9 for HOBr, 10 to the minus 11 for HOI. So it follows that trend. And then the last one we're going to deal with, so we have another if we have an oxo acid, so something like, it doesn't really matter, so that nitric acid or sulfuric acid or sulfurous acid, so sometimes there are a similar central atom, so say nitrogen or sulfur, but they also have different number of oxygens. Each one of them may be acidic. So the more oxygens per hydrogen for the same central atom, you have a stronger acid. Okay, and so what that basically the derivation is once again down to electronegativity. Oxygens tend to be pretty electronegative. If we put more of them around, say a nitrogen or a sulfur, it's going to pull more electron density away to those oxygens, away from a oxygen-hydrogen bond, making it more acidic. So the example is nitric acid, so HNO3, we could draw that out if we wanted, is a strong acid. It's one of our 7 strong acids that we need to remember. HNO2 is not in that list, and actually if we looked in the back of our book, we would find that there is a Ka for that shows that it's a weak acid. Okay, so one less oxygen, it goes from a strong acid in water to being a weak acid in water. So the takeaways from this video are basically anything that weakens the H, whatever element it's bonded to, oxygen, chlorine, and so forth, whatever weakens the HX bond leads to a stronger acid. And one way to weaken a bond is put an electronegative element nearby that pulls electron density away from it. That also makes it stronger. And ultimately, we also have math, right? So Ka, or actually if we go all the way back to our delta G, that's our measure of acid strength. So until next time.